In this and the next few videos, we'll discuss solidification. During the process of solidification, liquid will turn into solid. Therefore, we'll start by discussing nucleation of the solid phase in the liquid phase. There are two types of nucleation: homogeneous nucleation and heterogeneous nucleation. We'll start by talking about the homogeneous nucleation. Assume we have this liquid phase here. As you cool down, then the first solid phase will start to form in the liquid phase. Note that the solid phase just formed inside the liquid phase without the help of interfaces or defects. This is why the process is called homogeneous nucleation. The question we have next is which energies of the system will change during the process when we remove small amount of liquid and turn that into the solid phase. The first is the change of the energy for the liquid phase. Some liquid will turn into solid. Since we are losing the liquid phase, we put a minus sign here. The change of the energy for the liquid phase is simply delta VL, the change of the liquid volume multiplied by GVL, which is the free energy per unit volume of the liquid phase. Similarly, we have the change of the energy for the solid phase. Because initially we didn't have the solid phase, now we have it, so it's a positive term. The change of the energy for the solid phase is delta Vs, that's the volume change of the solid phase, multiplied by GVS. GVS is the free energy per unit volume of the solid phase. In addition to the solid phase, there's one more thing we're adding into the system, which is the solid-liquid interface. The change of energy for this interface can be expressed by delta ASL, that's the area of the interface multiplied by gamma SL. This is the solid to liquid phase interfacial energy. Now we can look at the overall change of the energy in the system. There are three components. The first is associated with the disappearance of small amount of the liquid phase. The second is the creation of the small amount of the solid phase. And the third is the introduction of the liquid-solid interface. Let's substitute what we had in the above three equations. Sorry, the E interface here should be delta A and gamma. We can assume the delta VL and the delta Vs are the same. That is to consider that whatever amount of liquid you are taking away will be replaced by the same amount of volume for the solid. Let's further assume the new solid phase is spherical. Then the volume change, delta V, is 4/3 pi r cubed delta GV. R is the radius of the new solid phase, and GV is the energy difference between the liquid and the solid phase. After that, we still have the interfacial energy, so 4 pi r squared, that's the surface area of the sphere, which is also the area of the interface, multiplied by gamma SL. If you have a closer look at this equation, you will notice there are two components. The first part is volumetric. What this describes is the overall energy decrease due to the solid phase consuming the liquid phase. This part favors solidification. The second part is the areal part. Now you're creating a new interface, and this costs energy. Therefore, this part acts as a penalty for solidification. Equipped with this knowledge, we can plot the volume part, surface part, and the overall delta G together. On the x-axis, that's r, which is the radius of the solid phase. On the y-axis, that's delta G. As the solid phase grows larger and larger, there is an overall decrease of the Gibbs free energy because the solid phase is at a lower energy state. So the curve decreases as R increases. At the same time, as R increases, the surface area for the liquid-solid interface also increases, and we know that acts as a penalty, so we have the energy increases as R increases. If you add these two curves together, you'll get something like this. Initially, as R increases, delta G increases, but after a critical point, delta G decreases as R further increases. We call this turning point the critical radius. The critical radius can be mathematically expressed by differentiating the above equation to get 2 times gamma over delta GV. Then what is the physical meaning of critical radius? If the solid phase has a radius greater than the critical radius, then the solid phase is stable. It can keep growing, and solidification will happen. If the solid phase has a radius smaller than the critical radius, then this solid phase is not stable and it will redissolve back into the liquid phase. We can also calculate the energy value at the critical radius. This is the energy barrier that nucleation has to overcome to achieve a stable nucleus. The value is 16 pi gamma square over 3 delta GV square. There's one important note I'd like to make here before we move on to the heterogeneous nucleation. For homogeneous nucleation, it is extremely difficult to happen in nature and in most of the material systems. Nearly all the nucleation events we observe in nature and in experiments, they result from heterogeneous nucleation, not homogeneous nucleation. Moving on to the heterogeneous nucleation, again we have the liquid phase and we have the solid phase growing from the liquid phase. But here we'll make one change. We have the mode present and we have this new interface here. Because of this mode liquid interface, the solid phase is more likely to nucleate on this interface. And this is the solid phase, and we can extend it into an imaginary sphere, and the radius of this sphere is r, or the diameter being 2r. There's also a contacting angle between the solid phase and the mode wall, and let's call that theta. Now we will ask ourselves again what energy changes we have when we nucleate this solid phase from the liquid phase. There is a reduction of the liquid phase volume, there is an increase in the solid phase volume, and also we introduce the solid-liquid interface. So the first three equations we can just copy and paste from the homogeneous case. In addition, we have two extra terms here. First, we have less liquid here, so the interface between the liquid and the mode decreases, and there is an energy change associated with that. Next, we have the new solid phase nucleated on the mode wall, so that introduces the solid mode interface, and also there is an energy associated with that. However, these two new terms have relatively small contribution, so we can approximate them to 0 and only focus on the pre-existing three terms. The final Gibbs free energy change as a function of radius is very similar to what you have seen just now in the homogeneous case. The first part is actually exactly the same. You have the volumetric part as well as the surface area part. Again, the volumetric part is due to the decrease in the liquid volume and increase in the solid volume. And again here, the same delta GV is equal to GVL minus GVS. And the surface area part is caused by the introduction of the new liquid-solid interface. Here comes the difference. At the end, you actually multiply the whole term by s theta. S theta can be considered as a correction factor. This is because you don't have the perfect sphere anymore. You only have a small segment of that sphere. Mathematically, S theta is equal to 2 plus cos theta, times 1 minus cos theta squared divided by 4. One property of the s theta function is that it is less than 1. Next, we can plot the change in Gibbs free energy as a function of radius of the solid phase. Again, on the x-axis, it's r, and on the y-axis, that's delta G. We can also plot the volumetric part and the surface part, and the end shape of the net change of the Gibbs free energy is very similar to what you have seen in the homogeneous nucleation case. You also have the critical radius, r star, and the energy barrier you have to overcome, delta G star. You may wonder, both the homogeneous and the heterogeneous nucleation cases, they look very similar, then what are the differences? Here, we'll cover both the similarity and the difference by doing the comparison. Let's plot delta G as a function of R for both the homogeneous and the heterogeneous nucleation cases in the same graph. Here is the homogeneous one, and the second is the heterogeneous one. Looking at the similarity first, both the heterogeneous and homogeneous cases, they share the same value of r star, the critical radius. We can tabulate it, and I will not read out the values. The difference between the homogeneous nucleation and the heterogeneous nucleation is pretty apparent. You can see the homogeneous case has a much higher energy barrier. The delta G star value is higher in the homogeneous case compared to the heterogeneous case. We already know the expression for delta G star for the homogeneous case, and we'll just write that down first. The heterogeneous case is actually very similar to the homogeneous case. We can just copy and paste. After copy and paste, all we have to do is to multiply this expression by s theta, the quote-unquote correction factor. We also know that as theta is less than 1, therefore the delta G star for the heterogeneous case is always smaller than the delta G star in the homogeneous case. I'll share with you some examples from my previous research when I was a PhD student, working with Professors Julie Carney and Simon Ringer. What you're looking at are atom probe data. Each dot you see represents one atom. If you look closely and carefully, in the first case on the left, the precipitates, they do not distribute randomly. They form certain lines. This is because the dislocations in the material act as a preferential nucleation site for heterogeneous nucleation. In the example on the right, you see a lot of carbides at the grain boundary, but not outside the grain boundary. In this case, the grain boundary is acting as the heterogeneous nucleation site for those carbides formation. I know these two examples are not solidification examples, but the fundamental science behind heterogeneous nucleation is the same as the cases in solidification. Last, I'd like to share with you one picture to illustrate nucleation events are happening everywhere, like in our lives. If you pour champagne, if you're over 21, or if you pour soft drinks, if you're under 21, into a clear glass, you will see a lot of bubbles forming. These bubbles do not form in the liquid. Instead, these bubbles form on the glass wall. This is because the liquid glass interface can act as a heterogeneous nucleation site for those bubbles. With a good understanding on nucleation, we're ready to take one more step further and look at growth as well as dendrite formation.